Long before gaming consoles had cheap, micro-sized Bluetooth keyboards with RGB lighting, the Atari VCS brought us the keyboard controller, video touchpad, and the kids controller. In this episode, we'll explore its origins and technical design, then show you how to bring these all to life in your own homebrew game. This channel is supported by viewers like you. Make a real difference today. Our patrons' monthly contributions, even just a few dollars, fuel the time, energy, and resources it takes to create quality episodes like this one. Join them now and be part of the making of the next episode. Thank you for being part of this journey. 10 months before the Atari VCS was released in 1977, the RCA Studio 2 beat it to market. It was pretty terrible, but it did feature two built-in 10-button keypads, possibly the first of its kind on a console game system. In hindsight, they may have been ahead of their time. Just a year later, the Magnavox Odyssey 2 debuted a built-in keyboard, and Atari took things a step further with the CX-50 detachable wired keyboard controllers. Soon after, Mattel's Intellivision included keypads directly on their hardwired joystick controllers in 1979. And a couple years later, the ColecoVision basically directly copied Intellivision with their implementation of the combination joystick keypad controllers in 1982. With the release of the bundled pair of CX-50 keyboard controllers in 1978, came three new games specifically created for the controllers. Brain Games, a collection of memory games where you need to remember the order of things, or button presses, like the game Simon. Codebreaker, up to 2 players where one creates a secret code. The other has 12 chances to crack it. And finally, Hunt and Score, which was strangely renamed as a game of concentration. You're given a field of squares and each turn you select 2 to see what's underneath. If you find the most matching pairs, then you win. In 1980, Atari released a version of basic programming for the VCS, presumably to better position the VCS as a competitor to computers, like the Apple II. Despite its utter terribleness, the basic programming box included the first button overlays for keyboard controllers. They featured visual markings of buttons or combinations of buttons to perform basic instructions like input, cursor movement, and menu navigation. The controllers could also slide together to form a single 24-button keyboard, allowing you to see all the functions in one place. To my knowledge, there's no other cards that benefit from the controllers sliding together. Additionally, basic programming would be the only game to use button overlays for the CX-50 keyboard controllers on the Atari VCS. Through 1982, a total of 8 games were compatible with the keyboard controllers, one of them being Star Raiders.
Watch out, Star Raider. You're flying in the Atari galaxy. We play rough out here. Sure, you have an attack computer and photon torpedoes. Ooh, nice shot, Flyboy. But there's 40 of us, only one of you. Checking the map, Star Raider? We know where you are. Bye-bye, Star Raider.
Star Raiders, the home video game that's only from Atari, and only for systems from Atari.
Star Raiders was first created for the Atari 8-bit line of computers in 1979, and later ported to the Atari VCS, now referred to as the Atari 2600, in 1982. While the game is fully compatible with the CX-50 keyboard controller, the game was actually bundled with the CX-21 video touchpad, a peripheral that was electronically exactly the same as the keyboard controller, with the only difference being the design of the outer shell. The video touchpad was created and marketed in 1979, but was never sold until it was included along with Star Raiders. In fact, it was never sold separately, and no additional button overlays were ever made for it, other than those included with Star Raiders. In 1983, Atari wanted to make the Atari 2600 more accessible to preschoolers, so in partnership with Sesame Street's parent company, the Children's Television Workshop, they released 4 games, along with yet another keypad controller, the CX-23 Kids Controller.
Announcing the new age of Atari. 3 to 7. Atari and Children's Computer Workshop, founded by the people who brought you Sesame Street, developed these new games for Atari's most affordable video game system, the 2600. They turned the 2600 into a center for learning important preschool skills.
2.
But don't tell your kids that. Just tell them about
Cookie Monster.
the Atari Sesame Street Library. a revolution in child's play.
This controller was much larger, with larger keypads for kids' smaller hands, and each of the games came packaged with a brightly covered overlay featuring Sesame Street characters on them. The CX-23 kids controllers are electronically the same as the other two inside the shell. The keyboard controller is a marvel of 1972 engineering, built around an electronic switch scanning matrix, a technology that has remained the foundation of virtually every keyboard ever since. Earlier keyboards were direct wired keys, where each key was individually connected to its own circuit. This design required a separate pin on the connector for every key, an impractical setup when you consider that a standard full-size keyboard has 104 keys. While modern keyboards typically connect via USB or wirelessly, their internal circuitry remains a complex web of circuit traces. A switch scanning matrix keyboard uses a wired grid of rows and columns. This is an example showing a single electronic switch to represent one key, and using one row and one column. We can add another switch in line on the first row by adding another column. Now, if switch 1 is pressed, column 1 is energized. Likewise, if switch 2 is pressed, column 2 is energized. We can easily expand our matrix to 4 switches by adding a second row. Now if we energize our second row and close switch 4, the second column is energized. Each row and column are wired directly to a corresponding pin on the DE9 connector that you plug into the back of the console. Pin 1 on the connector provides power to the first row, while pins 2, 3, and 4 are wired to the second, third, and fourth row. The first column is pin 5, second, pin 9, and the third, pin 6. The trick to determining in your code which of the buttons is pressed is by scanning through each row one at a time. When you detect an energized column, you use that column along with the currently energized row to determine which button was pressed. When we press button 1, we can see that pin 1 and pin 5 are energized. This is button 2, 3, 4, 5, 6, 7, 8, 9, star, 0, finally pound, hash, hashtag, sharp, or number sign, depending on the context or how old you are. Now that we know the hardware switches and pins, let's have a look at which registers handle each. Port A on the console is the left connector on the back of the Atari, player 1, or player 0 if you want to be technical, which I guess is why we're here, so let's go ahead and be nerds. Player 0's controller uses the first 4 most significant bits, D4 to D7, on switch A for each row. Interestingly enough, you might assume that you set the bit to 1 in order to energize a row, but you actually need to set it to 0, and all the other bits need to be 1. We read each column by checking bit D7 of the input 0 register for the first column, input 1 for the second column, input 4 for the third. The column is energized if bit D7 is set, or in other words, 1. On port B, player 1's controller uses the 4 least significant bits, D0 to D3, on switch A for each row. Each column is read by checking bit D7 again, but on the input 2 register for the first column, input 3 for the second, and input 5 for the third. At this point, we're going to need to piece all this together in the right order, or we're going to have ourselves a really bad day. The first step is setting the pins on the controller as output, so the console will supply power to them. This is done by writing to the switch A control register and setting the first 4 most significant bits to 1 for player 0's keyboard, and the least significant bits to 1 for player 1's keyboard. You could also just set all the bits to 1, since there's literally no downside when using the keyboard controllers. However, for learning purposes, the first example included in the episode specifically sets the bits depending on which controller we're checking. Now that we have our pins set for output, we can energize one of the rows using switch A, after which we need to wait for approximately 400 microseconds for the row to charge. If you don't, then you're not going to be able to read anything from the input registers. 400 microseconds is about 477 machine cycles, or just over 6 scan lines on the Atari 2600. Once the row is charged, we read the input registers one at a time to check if they're energized and bit 7 is set to 1. If we don't detect any key presses, then we start the sequence again by charging the next row, waiting 400 microseconds and checking the inputs, and so on, until we've checked all the buttons we're interested in. Realistically, you don't need to check every button. If you're only interested in a few, say the middle column with 2, 5, 8, and 0, then just check that column. Or maybe you only care about the first 2 rows. It's your game, do what makes sense for you. Now that we know the hardware registers and theory, let's have a look at the code. The example we're going to look at in this episode scans over both keyboard controllers and displays a graphic of the button you pressed. But first, we need to know how to configure the emulator to treat the input as the keyboard controllers. The following information will use a standard English 104-key PC keyboard. Your layout may be different depending on your computer type, location, and language, so please refer to your emulator software for more information on key binding. In the Stella emulator, which is the most common, you need to press the backtick key. This will bring up the debugger. From there, click on Options, Game Properties, and then select the Controllers tab. Click on the drop-down for left port and select Keyboard. Do the same for the right port if you want to try that side as well. On your computer keyboard, the left port uses the keys 1, 2, 3, Q, W, E, A, S, D, Z, X, and C. The right port uses 8, 9, 0, I, O, P, K, L, semicolon, comma, period, and /. Unfortunately, while Stella will remember your keyboard configuration after you save, it uses the signature of the ROM file to determine what configuration to use. When we're modifying our code, that signature is constantly changing. So you'll either have to keep setting it back to use the keyboard controllers each time, or use Stella's command line parameters to force it to use them. That's a little too heavy for this episode, but we'll cover it in more detail in future, where I'll show you some of the tricks and tools I use to make game development even easier. Be sure to subscribe and let me know if that's something you're interested in. But for now, let's get back to the code. First, we'll define which pins on each controller will be used as output. The first byte will set all the row pins on port A to output, and the second byte will set all the row pins on port B to input. While we're scanning the controllers, we'll swap between the two up here. This is where we select which byte to use, based on the Y register, which holds the index of the current controller. We store the byte into the switch A control register, which will configure the pins on the PIA, or peripheral interface adapter. Now we need to configure which row we want to energize. So back down to our data tables. Here we've defined 2 data tables to store the bytes for port A and port B. Each has 4 bytes, 1 for each row, with the first byte being the top row. As mentioned earlier, we energize a row by setting the corresponding bit to 0. We then set up the tables for use with a pointer, which will allow us to easily switch between which data tables we're reading without the need to hard-code the names of the tables everywhere they're being referenced. You can learn more about using pointers in our episode titled Animating Graphics on the Atari 2600. I'll leave a link in the episode's description. We use these data tables by selecting which table we're going to read from, again using the Y register, which represents the current controller, and then reading the byte representing the row we want to read. In this example, we start with row 3, the bottom row, and work our way down to 0, which is the top row. We usually try to decrement through a list because it's faster to check if a number becomes 0 or negative than it is to compare a number to another number. Once we have our byte, we store it in the switch A, and then wait about 400 microseconds while it starts to energize our row. We do this by killing some time and burning 6 scan lines with a WSync loop. However, if you had other things to do for your game, you can use these cycles for whatever you want. After 400 microseconds, we're clear to start reading the input registers. In this code, we're checking one controller at a time. So we check which controller is current and then jump to the correct lines. Since we're currently checking the controller in port A, we carry on to the next instruction. Checking the input registers is easy. We just load the register and check if the D7 bit is set to 1. Luckily, we have a handy branch instruction that checks for that. The BMI, or branch on result minus, checks the processor status negative flag, which is set when the result of the last operation was negative. Specifically, that bit 7 of the last operation was 1. If it's not, then we move on to the next input register, and then on to the next controller. But if it is, then we know that a key was pressed. We then use the row that we're currently on and the input detecting the key press to determine which graphic to display on the screen. The second example included with this episode performs the same function, but it finds some cleaner ways to code the key pulling routines. If you're wondering how the graphics are encoded in both examples, this will be included in a future episode, along with a tool I created to help me design and encode them. Be sure to subscribe to this channel to let me know if this is something you're interested in. While keyboards are the preferred input device for many PC gamers today, the situation was quite different for consoles in the early 1980s. Back then, the keyboard wasn't widely used in a meaningful way, especially on systems like the Atari 2600. Most games don't take advantage of it in any interesting or effective manner, with Star Raiders being a notable exception. What do you think would be an interesting way to incorporate the keyboard controllers in Atari 2600 game? Let me know in the comments below. As always, all the example code from our episodes is available in the repo. Just follow the link in the episode description. Have you programmed Atari today? That's all for now. Thanks for watching, and I'll catch you later.